Good day. All sites are now on the conference line in a listen-only mode. If anyone should require any assistance during the call today, please just press star and 0 on your touch-tone phone, and we do have operators and technicians standing by to help you. At this time, I would like to turn the conference over to your moderator, Mr. Don Forby from Mariah Bio. Please go ahead.
Thank you, Sarah, and welcome to everybody to Mariah Bio's second web seminar series for the MasterPlex Quantitative Analysis Software Package. I would like to thank you all for joining us this morning or afternoon, depending where you are. And just to answer a couple of preliminary questions for you is the web seminar going to be recorded so that you can listen to this in the future? And absolutely it will be. It will be on our website. Will you be able to get copies of the slides after the presentation? And again, yes, you will. It will be posted on the website, and or you can email Mariah Bio, and we can get that to you, and we'll give you that email address at the end of the presentation. Can you ask questions to the speakers? And we're going to hold all questions to the end, but then we'll have a question and answer period, which you'll be able to ask specific questions to the speaker. And can you get a demo or trial copy of the software if you don't already have one? And yes, again, it's on our website, and you can simply go there and download a copy of the software. So that answers a couple of preliminary questions. Again, I'd like to thank you all for attending, and right now I'm going to turn our discussion and presentation over to the lead presenter, who is Alan Min, the lead software programmer for MasterPlex QT. Thanks again, and Alan.
Good morning or good afternoon, everyone. My name is Alan Min, and I'm lead engineer for MasterPlex QT project here at Mariah Bio. And today we're going to talk about MasterPlex QT, advanced topics in MasterPlex QT, mainly focusing on calculation aspect of the software. And again, this is an advanced topic, so if you're looking for basic features and training, then we also have the recordings for the previous seminar, which you can download from our website. And overall, I would like to go over a general calibration process, and then interpolation and background subtraction, and how to interpret the results, and heteroscedasticity, and why you need to use weighting, and then wrap it up with the little demo on how to treat standard replicates. And as many of you knew this already, the calibration process is to interpolate unknowns from a set of known standard values, and the generally accepted models are 4- and 5-parameter logistic curves, and you can also extrapolate, not only interpolate but extrapolate. It is possible, but use with caution, and then we'll go over that caution later on. And before going into details about the calculation, I would like to give you a little review on 4-parameter logistic curve, because it makes a lot easier to understand what we're going to talk about when we get to the calculation. So anatomy of a 4PL curve. So we have a Cartesian plane, X and Y axes, and we have MFI on, usually we have MFI values on Y and concentrations on X. And we have our standard data points. These are the standard data that you obtain by running standard samples in the assay, and each point has MFI value with a corresponding known concentration value. So if you plot them out, so we have a plot that looks like a letter S, and that's why 4- and 5-parameter logistic curves are categorized as sigmoidal curve. In other words, it has letter S shape. So the curve is fitted, and the way the curve fits is determined by your data. So the curve always follow your data. And 4PL curve is called 4PL, 4 parameters, because it has 4 parameters, and the first parameter is parameter A, which is the baseline. And another parameter is parameter D, which is the upper bound of the curve, upper bound of the standard model. And then we have a midpoint between A and a D, And we can project that midpoint onto the curve and then project it down to it. So this is the inflection point, and we project from that point down to the concentration, and we have a parameter C. And we'll talk a little bit more about parameter C a bit later. And the slope at the inflection point is for parameter B, which determines how fast your reaction or whatever goes on at that point. So now we have parameter A, B, C, and D that help determine the shape of the full PL curve. And again, your data determine how the curve looks, and the way how the curve looks is related to the value of the parameter. So after you've fitted the curve, each of these parameters will have corresponding values, and these values are dictated by your standard data. And of all these parameters, we'll look at parameter A. What that looks like is it is basically your background. But the thing is that it's not. This value should not be confused with the background values that you obtain from the background wells that you run with your assays. And two values may not coincide. So this is basically based on the standard data giving, based on your data. A is the MFI value that gives 0.0 concentration, which is A is the background value predicted by your standard data, not by your background well. And two values, again, may or may not coincide. So in a perfect world, when there are no backgrounds, there are no noises during the detection, what we'll have is we'll have a zero background. So in that case, all of the data is here, and the curve, again, follow your data, and your baseline moves down to 0. So this is a perfect scenario where your background, the value from your background well will match the value from A, and they're both exactly 0. Okay? And as I promised, the parameter C basically is at the concentration that corresponds to the midpoint, the inflection point on the curve. So if you take the derivative of this standard data model, what you have is something like this. And your point C, the inflection point is right here. It's called inflection point because the reaction starts to slow down beginning from that point. So basically your corresponding point here, C is right there. The reason why it's important is because when you're doing dose response study, and this is the highest your reaction will go. So which is often referred to as ED50 or EC50 or LD50. So that's a little bit about parameter C. And we also have 5-parameter logistic curve, and it's identical to 4PL, except there is an extra parameter, E, that compensates for asymmetry part of the curve. So as I've mentioned, there's an inflection point, and the upper and lower part of the curve, 4PL curves are identical, meaning they are mirror image of one another. But with 5-parameter, that need not be the case. So if your data follows, and a lot of the time it does, the symmetric standard data, then you should use 5PL curve. I think we have most of the basics, so we'll go over. We'll continue on to interpolation and background subtraction. And again, interpolation is the process of using a standard data to read unknown values from the curve. In the past, I've spoken to many of you and a lot of users, and I've compiled a list of most commonly asked questions as far as the calculation process is concerned. So in this section, we'll cover some of those questions, and I hope that helps answer some of your questions. And one of them is, why are there negative MFI values? Because it doesn't make sense to detect negative values. So after I explain why that's the case, the next question is, well, if there are negative MFI values, why are negative MFI values giving positive concentration results? It doesn't make sense. If it is negative, it should give negative concentration. So we'll explain that. And the next is the out-of-range notation. So when a concentration cannot be calculated, we use a notation saying, something is less than something and something is greater than something, and a lot of the time people run into problems with those notations. And lastly, one of the latest questions is saying, well, if it is out of range, if something is out of range, then one sample is out of range, but because it's too low, but the sample right next to it has even lower concentration than that. And what's up with that? If it cannot be detected, if it's too low, how come the one next to it is even lower than that? So we'll help you understand that a little better. And first of all, we'll hit up with background subtraction. And again, we have X and Y coordinate systems. We have MFIs on Y, and we have concentrations on X. And we have our standard data. And the curve is fitted based on this data, so the curve always follows your data. And of course, the parameters of the curve also follow your data. So we have the parameter A, which is your background, your theoretical background. The background predicted by your standard data, not from your background well. So we have an MFI value on Y. We would like to get corresponding concentration. We project it onto the curve. When at the point where it intersects, we project it down, and we read off the unknown concentration from here. So that's all good. And now we begin subtracting background value. So when we're subtracting background value, what we're doing is we're basically subtracting a constant background. So, which means all of your standard sample points, standard data, shifted down because they have been left a constant value. And this constant value comes from your background wells that you run with the plate. So if you don't subtract background wells, they go up. If you subtract background values, they go down. And when the data go down, the curve follows your data. And so is the baseline. So now so does the baseline. And now, as you can see, the noise level is reduced. It used to be much higher than this. And again, this will never, ever be zero. In a perfect world, it will be zero, but we're not living in one. So you'll always have some values in here. So, again, this parameter value need not be the same. It will never be identical to the value that you get from your background well, because these are the ones predicted by your standard data, and your background well could have anomalies. Let's say there are some trash, deadlets, all kinds of anomaly with one background well that could throw off your background value. And let's say you have an unusually high background value due to one of these phenomena, whether it be trashes or deadlets or chemical reactions. That over-subtraction could occur, which means it could be subtracting more than it should. So in that case, in some of the cases, well, actually, when your MFI goes down, your unknown values will also go down. And when you interpolate, you'll have a new value move to the real value. But now, when the over-subtraction happens, we could have a scenario like this. So now the curve is in the negative MFI region. The bottom part of the curve is the negative MFI region. So again, the curve follows your data. It always follows your data, and so does your baseline. Okay? And now your baseline is right here. So if the MFI values just fall into that area, then you'll have a negative MFI value. Still the same, it's just being over-subtracted. So whenever you have a negative MFI values, check your background wells, background samples, and make sure that the value makes sense. If it is not, if you have multiple background wells, then try to eliminate those wells that are throwing the background value off the curve. And now we have another issue, which is now we have a negative MFI. Let's trying to get concentration values of that negative MFI. And guess what? We have a positive concentration. So how could that be the case? Because shouldn't negative have negative MFI value? Well, when you're tracking background, all you're doing is shifting curve up and down, not left and right. So your concentration region never shifted to the negative area. So the curve only moved down, up and down, in first and the fourth quadrants of the Cartesian plane. So your concentration remains positive, even though if you have oversubtraction. So things to look out for is if you have negative MFI values, check your background wells and make sure that there are no anomalies in there. And there are a lot of things that could happen, like I said, with the trashes, deblets, outliers, and all kinds of bad things. And the next is, well, you know, the software has all these little cute notation with the greater than and less than sign with some concentration values. I mean, these you know, what are those? I mean, those are out of range values. So the next question is, well, what happens when it's out of range? So there are two different out of range scenarios. The first scenario is when an MFI value is out of standard range, where standard range is defined between the highest and the lowest standard point. So this is the out of range that most of us understood. Okay? So when it says out of standard range, then it's, you know, it stays out of standard range. But there's also a second condition that most of us aren't aware of. The second condition is when MFI values fall out of an equation model's calculable range. So we'll give you a graphical representation of that. So we have a familiar picture here again. And then we have minimum and maximum standard data points that you get from the standard sample. And if we put a vertical line here and a vertical line there, everything outside of that region is out of standard range. And the lower part is lower than the lowest minimum concentration. The higher part is higher than the maximum concentration. So for those of you who are doing clinical diagnostic, you generally don't want to interpret data in this area. Anything that happens in between is interpolation. Everything that happens outside is extrapolation. And MasterPlex QT 2.0 doesn't care much about extrapolation or interpolation. It allows both. So it'll still give you the answers. But with extrapolation, it could be dangerous, and there are things that you should look out for, which we'll go over a little bit later on. The second condition also, second condition is determined by parameter A and B. So that's why we had to go over the anatomy of a full DL curve. So we have A and a D. Again, these are the upper and lower bound of the curve, and they're called horizontal asymptotes. Mathematically, that means the curve will never reach these bounds. They're not supposed to reach these bounds. It'll meet these bounds at infinity, which is forever. So anything outside, any MFI, not concentration, any MFI outside of this region is not calculable. And if it is lower than A, it's said to be MFI. Less than A, it can be calculated. If MFI greater than B. And so, well, next question is, well, why is that the case? Why can't they be calculated? Well, the equation model for a full parameter logistic curve is here. And basically that's, what it says is, if you have X, you get Y. You plug in X, you get Y value. If you have X, you get Y value. The only problem is that we don't have X. We have Y, but we want X. So we want the other direction. We have MFI, and we want concentration. But to do that, you have to have a slightly modified inverse function of the original one. It's basically a high school algebra. You just move terms around and you come up with this inverse formula. And the problem is, if Y is out of range, out of A or D, then the term inside the braces is reduced to a negative number. And that is raised to the power of a fraction, which is a root, and you can't take a root of a negative number. It's not mathematically possible, and therefore these values are said to be out of equation range. And it's not only MasterPlex QT cannot do it, nobody can do it. Well, at least not in this universe. And so nobody can do it. And again, I'll demonstrate one danger of extrapolation. So we have our usual curve here. We're going to blow up at the top portion of the curve. Okay, so now we have the top portion magnified here with that little triangle being the highest standard point. And let's look at two MFI values, one here and one right here. They're relatively close, maybe about 5 points in difference, 5 picogram per milliliter in difference. And if we look at the value for this, that's a problem. Because a slight change in Y will result in a huge jump in concentration. So if you have the data that you are willing to extrapolate, then be cautious. Because if the data is near the far end of the curve, things like this could happen. And again, MasterPlex QT does not prevent you from extrapolating the data, but that's fine. You can use it with your own judgment call. And again, extrapolation is dangerous because if it is used out of context, then you could have some real weird results. Okay. And okay, so now we understand why it is out of equation range, but we have to give it a name. So in the first version, we came up with this notation, which is this is in version 1.2, 1.0 and 1.2, and that actually confuses a lot of people more than it helps. And what's max and what's min, nobody knows. So that's gone. So instead of max and min, we could also plug in the real values. Let's say if A is 13.5, we could use, instead of min, we could use 13.5, and same thing with the upper part. And this is a little better, but that's not what we want to know. We don't want to know about MFI. We want to know about concentration. So this is better, but not terribly useful. So that's out of the question. It's not in the final version. And what we would like to know is some sort of indication in terms of concentration. And first, the concentration goes, we have 2 points that we know for sure exist. That's the minimum standard and the maximum standard. So the notation that we adopted is the one that a lot of people are using, which is to denote that concentration is greater than or less than minimum, maximum, and minimum standard concentration. So if you look at this point, what this point is saying is that it is the concentration of the sample cannot be calculated because it is out of equation model range. The best thing we can say about this point is that it is lower than the concentration for the lowest point. So that's basically all it says. And you could change the wording to greater than for the upper part. But so we have another question. Well, if we want to use less than or greater than, why not use absolute maximum and minimum values for the entire curve and not just the standard data point? The problem is that it can't be calculated because they're on A and D, and again, as I've mentioned, they can be calculated. And so basically this helps clarify the greater than and less than sign. And when we go to the software, I'll explain a little bit about the area where most people have questions. And the next part is heteroscedasticity, and I hate that word because I can never pronounce it without running out of breath. But basically what it says is it's a non-constant variability, and it rises in almost all kinds of fields, scientific field, and chemical and biochemical assays are no exception either. Basically what it means is the bigger the value that you're trying to measure, the more measurement error you make, and which is pretty logical. If you're measuring a large number, your standard deviation of CV could be relatively higher, so the error could be higher, and so which means the error is not constant, and it changes. And one way to look at it is by looking at the residual plot, and the residual plot is the plot of the residual on an XY plane. This is the screenshot from MasterPlex QT 2.0. Now, residuals are the difference between expected concentration and calculated concentration. And the higher the residual, the farther residual, the residual are higher at the higher part of the standard curve, split this slide, and then so now we have a funnel or wedge-shaped residual plot, and they usually indicate non-constant variability. So again, residuals are, this is another representation of residuals, and so we have the standard point. That's where you expect your standard concentration, which is right here. This is where you expect your standard concentration, but actually the one that you get is right here because that's where the curve falls. The difference between those two, the red line, is called residual, and which is related to the error. So what we have right now is, as you can see, residuals are relatively small here, but it gets higher at the higher end. So when something like that happens, if you put it on a plot like this, you'll have a funnel or wedge-shaped representation. Okay. Well, that's great, but why should you care about that? And the reason is that all curve-fitting algorithms, not only MasterPlex QT, all of the software packages, they are based on probability theories. And one of those theories assumes that all data points are measured the same way, meaning they all make the same error. They all have the same nature of error. So during curve fitting process, all standard samples are given equal freedom to influence the curve. So during the curve fitting, each point is pulling curves through their way so that it comes close to their point. The only problem is that those points with a higher error influence the curve more because they have, they have the most to lose because they have the highest residuals. So they pull the curve more to their way, and that leaves more accurate points at the lower bottom lose sensitivity. So we have a problem, so-called lack of sensitivity in lower part of the curve or concentration. So that's why you should be aware of that. And so now that's great. Now we're aware of that, but what are we going to do about it? And one way to counterbalance non-constant variability is to make them constant again. And to do this, we assign weights to each standard sample data point. And these weights are determined, approximated, based on the measurement errors. And by applying weighting, points in lower concentrations are giving, once again, more influence on the curve again, which it should be, because more accurate points should influence the curve more than less accurate points. In QT 2.0, we have 5 different ways to assign weights. 1 over y squared, basically it minimizes the residual, which is also, which is again related to errors based on relative MFI values. So, the higher you go up in y scale, the less weight you get. And 1 over y is another variation of 1 over y squared, but it works especially well if you have, if the errors if the errors follow Poisson distribution. And there are 2 more which is rarely used. Most of the time you don't want to use these. Well, we throw those in there so that they're consistent to other analysis packages, 1 over x and 1 over x squared. And that basically is based on concentration value, not on y value, but on x value. So it gives more weight to the left part of the graph than right. So x squared is kind of similar. It's another variation. And lastly, I put this in red because it's a double-edged sword. If you know how to use it, it could be helpful, but more often than not, it could get you, more erratic errors. And that is 1 over standard deviation squared. So if you know the exact error distribution and standard deviation for each point, each standard sample point, you can manually enter it into the software, and software will use this algorithm, and then select this algorithm, and software will use it to calculate. But do this only if you know the exact nature of the error distribution, because more often than not, if you use this, you won't be getting what you're expecting. And the reason is because there are disadvantages of weighting. In practice, we almost never know the exact values of the weight. That's because we never know the nature of the errors. If we know the nature of the errors, we wouldn't be fitting the curve. I mean, we wouldn't be guessing. So we have to guess these weights, and of course, results are as good as their initial guesses. So in practice, the small variation introduced by guessing these weights are proved to be negligible. So even if you're guessing, they won't cause much of a problem. But however, if you decided to use standard deviation, for example, let's say you had replicates fine for your standard data, and take mean, average, and standard deviation, and use that standard deviation as the weight. Okay, the results could go wild if you're using a small set of replicates. And basically, having 2 replicates is not going to do the job. Not even 3, not even 6, we're talking hundreds. If you do 100, then probably okay. And in that case, probably not practical to do it with the assay plate, because at some point, you do want to get your unknowns, not just standards. So keep in mind, again, we're giving you tools to do the stuff that you do. However way you want to use it is up to you. We're giving you where are the pitfalls. Right now, we're giving you information on which area that you should be careful and which area that you should avoid if possible. And the results of weighting, and this is a little breakdown that we did months ago. And the only thing that you should look at is the last 3 columns that use IPL with curve with weighting. And there are percent recovery values. And percent recovery is calculated divided by expected times 100, which is the measure of how good a standard curve is at that particular standard point. So if it is closer to 100, it's good. If it is more or way less than 100, it's not good. So as you can see, each column, each orange column, percent recovery value, it's okay up until the last 2. And then the last one is terrible. So, this is, again, because of the non-constant variability. So the values that your unknown values interpolated at that part of the curve are losing, 50, 60%, 60, 70% accuracy. So if we apply weighting in the left column, we can look at that, and the accuracy increases dramatically at the lower end without sacrificing overall accuracy of the curve. Again, if you look at it, we have numbers for 1.2 version, and there's a comparison between the previous version and 2.0, which is enhanced weighting algorithms, and the numbers are we tell the story here. And for references, you could, for a weighted least square regression about the weighting and all this stuff, you can go to NIST handbook. It's available over our website, and you can also go to perfit.com, which is maintained by Dr. Harvey Moltowski, and who also wrote a book called Intuitive Biostatistics, which is very user-friendly. I mean, it's really easy to read for scientists and biologists. And we have, if you want to dig up a little further into mathematics, you could go to transformation, weighting, regression, And if you're interested about computer algorithms, and there is a sample code, some numerical recipe in C. And what I'll do at this point is I'll go over the application to demonstrate how to actually apply weighting, all that good stuff. Okay. So I hope everyone is seeing, looking at the MasterPlex QT screen. So first of all, we'll load a CSV file. This is a file that we get from Luminex machine. It's really easy to look at it in 96 well-play format. We have analytes on the left side, so you can switch between different analytes and see the results change. You can view different data types, whether it be beat count or concentration or dilution or standard values or whatnot. And I have a template created just for this, and then we'll calculate. Okay, and now we'll look at the concentration. Okay, so this is the part that I was talking about, the less than or greater than sign. So what this means is it's, the concentration is what we can, best thing we can say about this concentration is that it's less than 22.22. But the confusion comes if you look at this point. Well, it says out of range, but the one above it is even lower than that one. So how come it can calculate 19.24 and it can't calculate something less than 22.22? So this is one confusion. And the way to solve that dilemma is not to think of it that way. Rephrase the way you look at it. And the problem is that we don't really know what that point is. Nobody knows. The only thing that we can say about it is that it's less than 22.2. It's not, again, it's what we're saying with this notation is that MFI value for sample E8 is so low that we don't know where it is. And the best thing we can say about it is that it is less than 22.22. Whereas for this guy, what we're saying is that, yeah, we know exactly where it is, and it's 19.24. So if you think of it that way, there won't be an ambiguity. And, okay. So we talked about negative MFI values. I wonder if we can find anything here. Probably not. Okay. Okay. So we'll look at the curve. So we have the curve, and you have your residual plot. Then if you look at residual plot, you have a funnel shape. It's very close to zero residual, or close to zero at the lower end, but they become higher at the higher end. So almost all standard curves have that shape. So this is probably okay, but this seems to be the outlier. So you could also use residual plots to pick outliers. If all points are close to the curve, but one is way out there, then you can identify that as an outlier. So we can look at standard data. Again, we can look at recovery data, and it goes bottom up. So higher values are at the bottom, and lower values are at the top. If you look at residual, percent recovery, it's all good at the beginning, it's good at the middle, and then it goes way off at the end, 163%. That's not acceptable. To remedy this, we're going to apply weighting. So I'm going to leave this open so that we could at least compare two. Okay, I'm going to open another same plate. Same template, except that we're going to assign weight here. Okay. So in this screen, we have a place called optimization, and you can check this if you want to use weighting, and you can assign one of 5 different algorithms. Most of the time, you'll be using 1 over y squared or 1 over y. Okay. And you'll rarely be using 1 over x squared, or, and then please don't use standard deviation if possible. And you can select this model for analyze, or you can actually fine-tune and find the best algorithm that you want for each curve. And we'll use 5-parameter logistic curve, and then assign model. When it's all good, we'll exit this, and then recalculate. Finish. So we can't tell the difference by looking at the picture, so we'll look at the data. We'll be looking at percent recovery values. So as you can see, 163 is improved to 102.45. That's a huge improvement. Okay, and 159 becomes 97.227, and 116. So you get the picture here. So by applying weightings, you could definitely increase the accuracy at the lower end of the curve, and you should. And the reason why that happens is because of that non-constant variability, and how to fix it is by using weighting. And we could go to different standard curves and compare that as well. This one is relatively good. Okay, but for this one, it used to be bad, but now it's better. Okay, this one is a good example. So you should, yeah, this one improved as well. Okay, this one didn't even show up. It's out of range. These were out of range. And it was so bad that they were out of range. In here, not only that they came back strong. So in some cases, if you have out of range value in the lower end of the curve, you may be able to use it with weighting. You may be able to bring them back up. But that will only work, again, if you don't have over background subtraction. Then if your background is messed up, then weighting won't even help. But in this case, it does, so everyone's happy. And so that's about weighting and how to use residual plot, how to use weighting. And not only that you can use weighting, you can also pick outliers, and then you can fine-tune it that way. So the curve that used to be really bad after you take outliers away and then apply weighting could become really good. That's that. Okay, one thing that I would like to mention is when you go to model equation, there is another option called fixed lower asymptote to 0, which means you can select this option if you trust your background value. So if your background value that you obtain from the background wells appear to be correct, then technically it should, after subtract from that value, you should have a 0 baseline. So you can emulate it by setting the baseline parameter A to 0. So if you check this, your A will be 0 regardless. But again, this will work if the backgrounds were not correct. So this could also bring in some of the out-of-range values back into back within range. But again, I would like to emphasize that we're giving all tools that you may need to do your research, your plate, your diagnostic, however way you want to use it. It's up to you. We're giving you information right now where and how to use it and what to look out for. And finally, I want to go over how to treat the background, replicate standards. This also appears to be one of the most common questions. Okay. Okay, so we have our standards. This is a plate full of standards, nothing but standards. Okay, and I have my template created for this. Okay, so what we have is, as you can see, the curve right now is using all points to fit the curve. And this option could be changed from here. If you go to Preferences, if you go to Calculation, you can select Average, whether or not to use average for individual points. And it explains to you what each option means. So you should use average, you should average standards, use the results to fit the standard curve if experimental errors are dependent on one another. And use the other one if they are independent. And most of the time, they are independent. So by default, MasterPlex QT will use individual points. And it's better because if your experimental errors are independent, then you have a smaller CV if you use this. But if you use another average standard, your error could be magnified and vice versa. So again, even if you select the other option, all points are going to still show up on the graph. Okay, because that's what the actual values are, and we never eliminate those values. They're still there, but you'll see that these parameter values are changed because of the different algorithms. So that's a little short demo about the calculation part, and I think that pretty much wraps up all the calculation issue with MasterPlex QT. So let me close this out. And okay. And again, you can get references if you would like to know more about these. You can go to the NIST handbook and all these great books. And we'd like to thank you for your time and participation today. If you'd like to reply to this webcast, there's the link. And if you would like to get a copy of today's presentation, you can email to this address, and we'll be happy to provide you with one. And we have our contact info, the phone number, and the email address. And with this, I would like to open question and answer. If you have any questions, please feel free to ask us. And please keep it general so that everyone can benefit from it. And but if you have any technical support issues, and then I would like to take them offline. I will be more than happy to help you with all of the technical support questions. So in here, we would like to keep it general to benefit everyone.
Thank you. If you would like to ask a question from your phone line, please press star and 1 on your touch-tone phone. If your question has been answered, you may withdraw it from the queue by pressing the pound key. Once again, if you would like to ask a question from your phone, please press star and 1. Okay, we do have a question from the site of Abigail Lozano. Please go ahead.
Hi, I just had a question about people using, this is probably a very basic question, about using mean versus median fluorescence intensity. Some people I've seen just use mean, and I think I saw that documented before in the journal article, but I've been noticing a lot more people are using median. I know ideally they should be the same, but I was wondering what your thoughts were on this.
It's more of I think the Luminex folks will be able to answer that better than I do, but the information that I have from them is that, when you're running the acquisition, you're looking at only only the region where your beats are. But there are a whole lot of other things going on that you don't see that are outside of the gates, okay? So, there could be trashes, there could be doublets, and everything that is eliminated nicely by your double discriminator gates and all the good stuff. But nevertheless, they're still there, and the final calculation could be influenced by those outlier values. So if you have an average, and if you have a really way out point, then your average will shift to that point. Okay. Whereas if you pick median, it doesn't get deterred by that outlier value.
Okay.
Okay. And especially with the Luminex, what we're doing is we're counting. We're basically, all the data are based on the count. So when you're counting, median becomes more important than the mean. Does it kind of help you understand a little bit?
Yes.
Yeah.
So when you do like the double discriminator, that doesn't necessarily take out all the doublets or the trash.
No, it does, but there are still outlier values even with that.
Okay.
Okay. So yeah, we'll contact Luminex for further information. I mean, that will probably be the same answer that it will give you.
Okay. Thank you.
Okay. Thanks.
Thank you. Once again, to ask a question from your phone, please press star and 1. And we'll take just a moment for any questions to register. And it looks like we have no further questions from the phone lines at this point.
Okay, great. So once again, I would like to thank you again, and hope to meet you again in future seminars. Thank you. Thank you.
Thank you. This concludes today's conference. You may disconnect at any time. Thank you for attending, and everyone have a great day.